It's a bipartite graph is a graph where you can like partition the nodes in two parts, two sets, where you always have all the edges that will go from one set to another. So you will not have an edge, let's say, from here to here inside one set. So all the edges will be connecting nodes from one set to another. If you have this, we call it a bipartite graph. In fact, if you have this and you want to solve this problem, then you need to construct a matrix, okay, that will represent all the edges. I don't know if you did this in another course. This is what we call the incidence matrix. It's a matrix that will give the edges in here and the nodes in here. So you will give numbers to the nodes, let's say 1, or even, I don't know, A, B, C, D, E, F, and for the edges as well, let's say A, B, C, D, E. So A, no, sorry, the node is big A, so A, B, C, etc., and A, B, C, etc. So if A is connected to A, okay, now you can have orientations also. If A is connected to A with the orientation from A to A, it will be 1 in here. Okay? If A is connected sorry, if I said if A is connected, sorry. If A has an edge A, so it will be 1. If it doesn't have an edge, let's say for the edge C is not connected with A, so it have zeros in here. C, D, E, because these edges are not connected to A. Okay? Etc. So this is the incidence matrix. The incidence matrix of a bipartite graph, for example, it's a totally unimodular matrix. So if you take any determinant, it will be 1, minus 1, or 0. So if you are solving such a problem and your matrix is the incidence matrix, then it's the case. All the vertices of P will have integer coordinates, then your problem will have a solution with integer coordinates. Okay? Yeah, that's an example. So, when you want to find a solution for a maximal flow problems, okay, with integer capacities, then the matrix will be a totally unimodular matrix. So immediately your problem will have a solution with integer coordinates. Okay? Another example, it's the bipartite graph. So this is an oriented graph. Okay? This one is not oriented, but also, so if you want to solve a transportation problem, so when your transportation problem, when you're presented like in a graph form and you put your incidence matrix, then you'll be able to construct a problem having a totally unimodular matrix as the matrix of as the A matrix in the linear program. So that your solution will be immediately a solution with integer coordinates. Okay, so this is one set of problems where you can have solutions with integer coordinates. But what about the other set? What about the case when you don't have a unimodular matrix? What should you do? This is where we introduce now the cutting plane algorithm. So the cutting plane algorithm, I go back now to what I explained in the beginning. So I have to take my domain and make cuts of the domains in a way to remove parts that are not necessary for my problem. Any questions? Questions? No? Okay. So the cutting plane algorithm. One moment. So the cutting plane algorithm. In the cutting plane algorithm, we need, as I said, to find cuts of my domains to remove parts that are not necessary for my problem. Cuts where you don't have integer coordinates, 1, and 2, of course, where my solution will not be lying. Okay, so this was developed by Ralph Gomory in '58. So I go back to the geometric idea I explained before. In fact, if the gray area here is your domain, you can notice immediately that. Oh, what can I draw? I'm not able to draw. Why not? Okay, so you can notice immediately that this part of your domain is a part where you don't have any integral coordinate, right? This part of your domain is a part where you don't have any integer coordinates. This part as well. You see? Okay, no, sorry, I missed one point. It's in here. So if you go like this and like this, so you only remove part where you don't have integer coordinates. So the idea is like this: is to find step by step cutting planes, cutting parts where you can remove these blue areas, but step by step. We cannot remove them in one step, all of them, because maybe if you remove one of them, okay, let's say that the maximum point will be reached at I don't know, this the maximum value of the function will be reached at this point. So maybe by introducing one cut like this, you will have a corner that will have integer coordinates. Then your problem will have this point as a solution, and you don't need to make the other cuts. Is that clear? That's very important. Is that clear? So when you do cuts, you are not forced to do all the possible cuts, but at least step by step cutting planes will lead you to step by step to corner with integer coordinates. And whenever you find a solution at a point with integer coordinates, you're done. You don't need to make the other cutting planes. Okay? So the idea now is to learn how to find these cutting planes and how to choose them in the optimal way, let's say, maybe to find the solution before doing all the cutting planes. Okay? So this is how it will be presented. So given a linear integer linear program, we take the React problem. So we remove the conditions where the variables should be integer, and then we solve it using the simplex algorithm. If the solution you find is a solution with integer coordinates, you're done. Okay? If not, you have to do a cutting plane. What's a cutting plane? How to introduce a cutting plane here? A cutting plane, let's say here, it's a straight line. So it's like you know that this straight line here and this one, where are they coming from? They represent two constraints, right? Two conditions. So if you have two conditions presenting these two straight lines, then adding a straight line will be like adding a constraint. That's why we're saying here, if your solution is not integer, then you introduce an additional constraint, which I call the cutting plane, such that what should this constraint satisfy? First, the constraints it's satisfied by all the points with integer coordinates. So if you introduce the red cutting here, okay, all the integer coordinates that I have inside will not have a problem with this cutting plane. So they will still be inside my domain. They will satisfy this condition. So if I say, yeah, the points I'm looking for are points that have their ordinate below this level. Yeah, it's fine. All the integer points here have their ordinate below this level. So if I add this condition, all the points with integer coordinates can still satisfy this condition. So they are still considered as acceptable points in my problem. Okay? So this is the first condition for the cutting plane. The second one, the constraint is not satisfied by the solution of the React problem. So I go back here, I will remove what I drew, and I will start back to explain this condition. So let's say we solve our problem and you find this point as solution. This point is not a point with integer coordinates. if you look closely, okay, it's not this point here. No, it's below it. So it's not a point with integer coordinates. That's why I will not introduce a cutting plane that is, let's say, in here. It doesn't make sense. Because if you do this, what will happen? If you do this and then you solve again your problem, if you remove this part and you solve again your problem, what will happen? You might find again this point as the point that will maximize your problem. Okay, so the cutting plane you add, it should first keep all the integer points inside, but also the point that was solution to your relaxed problem, it should be removed from your new domain. So the cutting plane I will introduce in this case is this one. So I will remove this part where I don't have any integer coordinates, and then I will remove the point that was the solution for my relaxed problem. Okay, any questions? Sorry? Yes.
Could you, I think I missed the bit where you explained it. Could you re-clarify what are the non-integral coordinates?
The non-integer coordinates?
Yeah.
I need to understand your question better. You mean what does the word means, or
Yeah, it's like I don't understand. It says that we make cutting planes to exclude non-integral coordinates. But what are those that we recognize them?
what do you say at the end?
How do you recognize them?
They are the points whose abscissa and ordinate are integer numbers. So they are the points that have the points highlighted here. See these points. Okay? It's fine?
Yeah.
That's your question?
So those are the integer points.
Yeah. So when I say integer points, it's only to say it briefly, but it's the exact rule is the points with integer coordinates. Okay? So
Okay. And why do we exclude those that are not integer coordinates?
because in my problem in the beginning I said I will be maximizing a function such that you have constraint number 1, number 2, number 3, and at the end you have a condition saying x1, x2, x3, whatever should be in n. So if you find a point whose coordinates, let's say if you find a solution whose coordinates are 5/2, 3, 4, that's not a point with integer coordinates because it doesn't have an integer here at this place. So this point doesn't satisfy this condition. So it's not acceptable.
Okay, that's what I missed. I missed this small detail.
Okay.
Yeah, because I thought we had to delete every point which are not integer below, make an infinity of them. Okay.
No. In fact, I will repeat what I just explained. So let's say you have this problem. You solve it. You find this point as a solution. This point, it has its, I don't know, ordinate that is not integer. Okay? So it's not an acceptable point for my problem. But it's the point that will maximize my function. Yes, I agree. On this domain. But it's not the point I'm looking for. So that's why I will introduce so I will put a new constraint. This constraint will say, okay, you don't take anymore all the points that are above this thread line. So you remove basically all these points. In fact, I don't care about these points because even if the solution is in this area, it will not have integer coordinates. All the points in here doesn't have integer coordinates. They have their y, their ordinate, between, I don't know, 1, 2, 3, 4, between 4 and 5. So it's not integer. So I have to remove all this area, as well as the point that was solution to my problem, and to solve my problem again on this new reduced area, hoping that that the solution will always be one corner of your domain. So hoping that maybe my solution now will be this point. Hoping. Now I will solve the problem. Now maybe I find out that now my solution is not here anymore, it's here, which doesn't have integer coordinates. So I will introduce a new cut, a new straight line that might be, I don't know, in here maybe, that will remove all this part that doesn't have integer coordinates, hoping again that my solution will be here, because that's an integer coordinate as a corner. Okay, but in fact no, I will solve it again. I will find that my solution is here, this corner, which doesn't have integer coordinates. I will introduce a new cutting, maybe from here to here. Oh, you see, always I will do the cutting always anyway to exclude the point that was solution and exclude an area that doesn't contain any integer coordinates. I will keep inside only the integer coordinates. So now I have, you see, every time I'm introducing a plane, I'm having more and more corners with integer coordinates. So now this corner is with integer coordinates, this one, and this one, and this one. I will solve my problem, hoping to find now a solution, let's say this one with integer coordinates. If it's the case, then I'm done. If not, I will continue, because I still have a corner here with not integer coordinates. So I will introduce one more cutting plane, maybe. Is that clear? Any questions? Okay, so that's the idea of solving an integer linear program. Okay, so the question now that we still need to learn is how to make this cutting, how to introduce this condition, or how to formulate, how to find the equation that will introduce this cutting. And this is what you will be doing in the exercises, in fact. And it's what I will do now is the part that you will be doing in the exercises, is the part where you introduce the cutting plane. So before I continue, I will tell you one thing. So you think that the problems you used to do in the last chapter were long, right? Because we used to solve a simplex method where you put the matrix, you do the echelon form, you find a feasible point, then you, if it's not enough, you continue, etc. So in the context of this chapter, when you want to solve an integer linear program, in fact, you have to do the simplex algorithm that you did in the last chapter, okay, at each step. So you solve all the simplex method. You do all the simplex method to find a solution. It's not a good one. You do a cutting plane, and then you will redo the simplex method again. So in each exercise of this chapter, you will be doing 2, 3, 4 exercises of the last chapter. 2, 3, 4 calculations of the last chapter to find your solution. Okay? Any questions?